When we gaze into the vastness of the cosmos, the wonders of our solar system captivate us. Among its treasures are the enigmatic dwarf planets, celestial bodies that tell a story as old as time itself. These small yet fascinating worlds hold clues to our solar system's formation and evolution. Today, we embark on a journey to uncover the origins of these mysterious worlds, unraveling their secrets one layer at a time. As they delve deeper, we will explore not only their physical characteristics, but also their profound implications for the history of our cosmic neighborhood. Their stories will lead us to insights about the dynamic forces and intricate processes that shaped the planets, moons, and even our own Earth. To understand the birth of dwarf planets, we must travel back 4.6 billion years to the dawn of the solar system. At this time, a massive cloud of gas and dust began to collapse under its own gravity, giving rise to a spinning disk of material. This protoplanetary disk became the cradle for planets, moons, and yes, dwarf planets. Within this swirling chaos, the seeds of worlds, both large and small, were sown. It was here, amidst the interplay of forces, that the first whispers of cosmic structure began to emerge. The collapse of this primordial cloud, known as the solar nebula, was triggered by a supernova shockwave, a cataclysmic explosion from a nearby dying star. This event not only compressed the cloud but also seeded it with heavier elements like iron, nickel, and other essential materials for planetary formation. As the disk spun faster, it flattened into a plane, concentrating in regions where planets and other bodies would eventually emerge. The interplay of gravity, pressure, and motion created a dynamic environment teeming with possibilities, setting the stage for the formation of diverse celestial bodies. The solar nebula's temperature gradient played a critical role in shaping its contents. Close to the Sun, intense heat caused volatile compounds to vaporize, leaving behind rocky materials. Farther out, cooler temperatures allowed ices and gases to persist, creating a stark contrast in the composition of inner and outer solar system bodies. This diversity of conditions laid the foundation for the incredible variety of celestial objects we observe today. The differentiation between the rocky inner planets and icy outer bodies was a key factor in the unique development of celestial objects, including dwarf planets. Additionally, magnetic fields and turbulence within the disk influenced the motion and aggregation of particles. Regions of higher density became hotspots for accretion, where planetesimals, the building blocks of planets, began to form. These initial steps were marked by countless collisions, as particles coalesced under gravity, forming the precursors to worlds. Within this disk, tiny particles of rock and ice collided and stuck together, forming larger bodies called planetesimals. Over millions of years, these planetesimals either grew into full-fledged planets or were scattered by the gravitational influence of larger neighbors. But some, unable to clear their orbits, became what we now call dwarf planets, frozen relics of a bygone era. These remnants serve as time capsules, preserving the conditions and processes of the early solar system. The process of accretion, the gradual accumulation of particles into larger bodies, was a complex and uneven phenomenon. In regions where material was sparse or gravitational interactions were disruptive, planetesimals remained small or fragmented. However, in certain pockets of the solar system, these bodies grew into protoplanets, some of which evolved into dwarf planets. Their formation was a testament to the delicate balance of forces within the protoplanetary disk. The Kuiper Belt and Asteroid Belt are key regions where these remnants still exist. In the Kuiper Belt, icy bodies like Pluto and Haumea formed under the influence of cold, distant conditions. Meanwhile, Ceres, residing in the asteroid belt, emerged in a zone dominated by rocky material. These environments not only determined their compositions, but also influenced their subsequent geological evolution. This distinction underscores the diversity of the processes that led to the formation of these fascinating worlds. Moreover, as these planetesimals interacted with nearby growing planets. Some were ejected to distant orbits or pulled into resonances. These gravitational dances added complexity to the formation and distribution of dwarf planets. In 2006, the International Astronomical Union defined a dwarf planet as a celestial body that orbits the Sun, has enough mass to achieve a nearly round shape, but has not cleared its orbit of other debris. 5 officially recognized dwarf planets: Pluto, Eris, Haumea, Makemake, and Ceres. Each have unique characteristics that reflect their formation historique. Yet, they share this common trait. They represent a middle ground between full-fledged planets and smaller bodies like comets and asteroids. The distinction between planets and dwarf planets is not just a matter of size. Clearing an orbit requires significant gravitational dominance, which most dwarf planets lack due to their relatively small mass. This limitation underscores their role as relics of the solar system's early days, when chaotic interactions were the norm. Their tilted orbits and elongated trajectories reveal clues about their past encounters with larger celestial bodies. Such interactions likely ejected them into their current positions, adding to their allure as windows into the dynamic processes that shaped our solar system. Each orbit tells a story of gravitational ballet, a record of near misses, collisions, and ejections that shaped their destiny. Pluto, once considered the 9th planet, resides in the Kuiper Belt, a region beyond Neptune filled with icy bodies. Its journey began in the outer reaches of the solar system, where lower temperatures allowed volatile compounds like methane and nitrogen to freeze. Pluto's intricate surface features, including its heart-shaped glacier, hint at a dynamic geological history shaped by internal heat and possible subsurface oceans. Pluto's demotion to dwarf planet status in 2006 ignited debates among scientists and the public alike. However, this reclassification provided clarity in how we understand celestial bodies. Pluto is not alone in its region. It is one of hundreds, if not thousands, of icy worlds within the Kuiper Belt. Its largest moon, Charon, forms a unique binary system with Pluto, as the two bodies orbit a common center of gravity outside of Pluto itself. This relationship has profound implications for our understanding of orbital mechanics and tidal interactions. Pluto's atmosphere, composed primarily of nitrogen, expands and contracts depending on its distance from the Sun, a phenomenon that continues to fascinate researchers. In 2015, NASA's New Horizons mission provided a treasure trove of data, revealing complex surface features such as towering ice mountains, vast nitrogen plains, and potential cryovolcanoes. These findings suggest that Pluto is not a static, frozen world, but one that continues to evolve, driven by internal heat sources and external interactions. Its dynamic weather patterns and seasonal changes further emphasize its complexity as a celestial body. The data from this mission has reshaped our understanding of icy worlds, inspiring further exploration into other dwarf planets. While Pluto and Eris capture much attention, they are only the beginning. The solar system is brimming with potential dwarf planets, each with its unique story. Worlds like Haumea, with its elongated shape and fast rotation, or Makemake, known for its bright, icy surface, showcase the diversity among these celestial bodies. These worlds are not merely frozen relics, but active laboratories where the forces of nature continue to shape their evolution. They challenge us to refine our understanding of planetary science and inspire curiosity about the unexplored frontiers of our solar system. The dwarf planets may be small, but their stories are grand. They remind us that even the tiniest objects in the cosmos can hold the keys to understanding our place in the universe. Thank you for joining us on this journey. Don't forget to like, subscribe, and hit the notification bell for more explorations of space, nature, and life.